Alright, for this next example we're going to look at this one's a carbon-14 dating problem. And so it says skeletons were found at a construction site in San Francisco in 1989. The skeletons contained 88% of the expected amount of carbon-14 found in a living person. Now, just as a bit of background, when a person dies, the carbon-14 stops replenishing itself from the food that they're eating, and so it starts to decay. Now, it's always been decaying, but a living person will continue to consume carbon-14. When they die, they stop that process, so then it only decays, and that's how they determine that. So, in 1989, then, how old were the skeletons? Okay, so a living person has a certain amount of carbon-14 in them. We'll call that 100%. Then in 1989, these skeletons were found with 80% in it, or in them. So how old were they? That's the question. One very important piece of information is the fact that the half-life of carbon-14 is 5,715 years. That's a long time. However, it does give us a point of reference now in order to set up our formula. So remember, when we did this in the last example, we started out with A for the final amount, A sub 0 for the initial value. Half-life has a base of 1/2. And then our exponent was time in years, well, it'll be years this time, time in years divided by the half-life. Okay, so it's time divided by 5715. And we divide by the half-life once again because if you plug in 5715 in for time, divide by itself, you get 1, and that's 1 half-life, which means you're raising the half to the 1 power and multiplying by just that 1/2. So that's how that works out. Okay, so now really all we have to do is figure out what A and A sub 0 are, plug those in and solve for T. Well, A and A sub 0 come from our percentages. So the final amount is 88%. The initial amount was 100%. Now, I'm just thinking about this. One very big mistake that students tend to make is they try to combine the 100 and the half. You cannot do that. Remember, order of operations says you have to do the exponent before you can multiply, and here we can't perform this exponent because of the variable. So we have to get rid of the 100. We can't do the multiplication, so we've got to get rid of it. So to solve this equation, we're going to start out by dividing both sides by 100. And then that's going to cancel out on the right. Then 88 over 100 is 0.88. And then we have 1/2 raised to the t over 5715. Okay, at this point I'm going to take the natural log of both sides. Remember I said we're going to apply a log to both sides, and we'll tend to use the natural log in this section. It doesn't really matter, you get the same answer regardless of what base you use on the logarithm, but we'll just we'll go with the natural log here. Now remember, there was a property for logarithms that says the exponent comes out front, and so we end up with the natural log of 0.88 equal t over 5715 times the natural log of 1/2. To solve this for t, we're going to multiply both sides by 5715. Alright, they will cancel off on the right. And I'll be left with 5715 times the natural log of 0.88 equals t times the natural log of a half. And if I divide both sides by that natural log of 1/2, I should be able to then isolate the t. Okay, so these cancel off. And that means t is by itself. T will equal 5715 times the natural log of 0.88 over the natural log of 1/2. When we calculate that, you can put that in the calculator. I'll run through that. 5715 times the natural log of 0.88 divided by the natural log of 1/2. And that gives me 1050, about 1054 years if I round that off. Okay, 1054. All right, so 1054 years. So that's how long those skeletons had been dead for. Interesting. Now, your textbook asks you to use a different model. I'm going to run through an example of using that model. It will give you the same answer, or roughly the same answer. I just want to show you how that works real quick. The model they want you to use is A equals A sub 0, and then they're going to use a base of E instead of 1/2. And so it's E to the minus 0.000121 t. Now that multiplier on the t is kind of a weird multiplier, plus you're switching the base to an E instead of a half. But the rest of this is really going to be the same idea. You start out with the 88 on the left and the 100 as your initial value, and then you just solve the rest of this for t. Now the book, actually in this section, the book comes up with this formula for carbon 14. Basically the 1/2 raised to the 1 over 5715 power is equal to e to the negative 0.000121 power. Those two are the same thing, and they show the conversion from one to the other. I personally like this one better, but your textbook wants you to go through that one. So we'll just go through it. You can choose. It doesn't matter to me which one you use. Alright, so at this point I would, again, following the same steps basically, divide out the 100. They cancel on the right. And I end up with 0.88 equals e to the negative 0.000121 t. Just like before, I'm going to apply a natural log to both sides, so it's natural log of 0.88 equals natural log of e to the minus 0.000121 t. It's almost too small to see, isn't it? I can't help it, I'm running out of room. And then we're going to take the logarithm property that takes our power and moves it out front. So this becomes the natural log 0.88 equals all that stuff times the natural log of e. Well, the natural log of e, if you don't remember, that's actually equal to 1. And so, because the base and the argument are the same. And so what I really have is just the natural log of 0.88 equals negative 0.000121 t. And if I divide both sides at this point by the negative 0.000121, I should get t by itself. So all that stuff cancels on the right. And I get t equals ln 0.88 over negative 0.000121, which if I throw that in the calculator, let's see, that would be the natural log of 0.88 divided by negative 0.000121. What you'll find is almost the exact same value we had before. Calculator says 1056 years. Okay, so it's off by what, 2 years over a span of over 1,000 years. So 2-year difference there, probably not that meaningful. Basically what's going on there is there's a rounding error. The formula that the textbook created here is a rounded value, and these are exact values. So I think my answer will be a little bit more precise than the one the book gives, just because of the rounding error in creating this model. Okay, but essentially the same answer is given in both cases.